times f of m dx. And it equals 0 for n, which means it equals 0 for n not equal to m.
Right.
And it equals 1 for m equal to n.
So why is that the delta function?
That's what it's defined as.
That's how it's defined.
Oh, okay.
All right. So when n equals m, that's like cosine of 3x and cosine of 3x. Those are essentially parallel in the connection to the vector space. But if you have cosine of 2x and cosine of 3x, what are those called? Those are the equivalent of orthogonal in function space, because what happens to their dot product? It equals 0.
So now, can you put that all together and talk about Hilbert space now?
So the solution, separable solutions, okay, will always have this property. Separable solutions are all good up to there. You get a nice infinite basis set. So separation of variables is a great way to solve partial differential equations. All right, but what guarantees this? And I've talked about this several times now. This is guaranteed not for all partial differential equations, but it's guaranteed for square integral solutions. This is true. This is true for square integral. Square integral. Square dash integral. Square dash integral.
What is that?
All right. And what is square integral solutions? Those happen to be the solutions to whose equation? Schrodinger's equation, because those have the probabilistic interpretation.
But so what is a Hilbert space?
So Hilbert space is all of this. It requires both of these. So Hilberts are infinitely dimensioned function spaces with all the properties of vector spaces, which means that they have a defined inner product, that works like that. And therefore, our solution to Schrodinger's equation is square integrable?
Yeah.
They better be. Did we do it by separation of variables?
Yep.
Yeah. So what type of solutions do we have to Schrodinger's equation? They are
Hilbert spaces.
Hilbert spaces.
And that's beautiful because it helps us in like labs and stuff fit anything we want it to fit.
So this is the biggest idea with Hilbert spaces, is that Hilbert spaces, if you have functions that have all the properties of vectors, then you can stop talking about them in terms of functions and just write them in terms of vectors, right? And if you write this whole problem in terms of vectors, what have you just done?
Just showing which ones are linear independent.
No, whose formulas of quantum mechanics?
That's Heisenberg's matrix.
You've done Heisenberg's matrix.
So the matrix mechanics of all this is quantum mechanics in vector space?
Yeah. No, not quite. This is how
Hilbert space.
This is how that Schrodinger proved that his wave equation formalism was equivalent to Heisenberg's matrix.
That's exactly right. That they're essentially different representations of the same problem. So instead of writing things in Cartesian coordinates, one of them wrote it in spherical coordinates.
Yeah, right.
All right. So how many people feel we did way more detail than I wanted to do? Trust me.
Well, I'll tell you, that was the first time you would have said that. It clicked.
It's not the first time I've ever said it. Trust me.
No, it's the first time. No, I know. What I'm saying it's the first time it like gel.
Okay. How many people feel a little bit better today? Matt? A little bit.